Iniziamo allora. Dunque, per fortuna dopo vari anni riusciamo a fare in presenza alla cerimonia di premiazione del premio Paladin, che quest'anno viene attribuito ogni anno dalla nascita della SIFS alla miglior tesi dottorale nel settore della meccanica statistica dei sistemi complessi. E quindi oggi qui nell'aula Max del Dipartimento di Fisica a Parma procederemo alla breve cerimonia di premiazione e poi al seminario del vincitore, che è risultato, come espresso nel verbale della commissione giudicatrice composta da Elisa Ercolessi, Guido Caldarelli e Eugenio Lippiello, il dottor Mancastroppa dell'Università di Parma, attualmente però ormai in forza al CPT di Marsiglia. La motivazione che la Commissione ha riportato nel verbale dell'attribuzione di questo premio è per la qualità dell'esposizione, per i risultati conseguiti e per l'impatto anche esteso al di fuori del campo della meccanica statistica. In tale tesi si è particolarmente apprezzata la capacità di alternare metodologie di carattere analitico e numerico, il confronto con i dati sperimentali, la descrizione delle attività svolte all'interno del campo di ricerca in generale. Il tema è appunto quello che poi sarà oggetto del seminario e riguarda appunto processi epidemici e su dei network adattivi temporali. Questo diciamo testimonia ancora una volta come nell'ambito della nostra disciplina le attività anche dei giovani si orientino sempre più in direzioni che stanno all'interfaccia anche tra aree che non sono strettamente collegate alla fisica. E questo è un dato caratteristico che mi piace molto sottolineare anche in queste occasioni, perché mi sembra debba essere considerato un aspetto che è proprio un valore aggiunto di questo tipo di area culturale della fisica. Ovviamente mi corre l'obbligo, prima di passare alla parte scientifica, di ringraziare i membri della commissione che hanno fatto un lavoro anche abbastanza, diciamo, pesante, perché sono dovuti leggere le tesi, valutarle, confrontarsi, scrivere dei verbali, farceli pervenire e quindi vanno tutti quanti ringraziati per la loro capacità e disponibilità. E poi ovviamente mi corre, anche se brevemente, commemorare comunque la figura di Giovanni Paladin, a cui è dedicato questo premio fin dall'inizio. Quando la giunta esecutiva della SIFS decise di istituire questo premio, fu quasi naturale per tutti pensare a intitolarlo al nome di Giovanni, che diciamo è stato un compagno di lavoro, di viaggio per molti di noi, sicuramente quelli di una certa generazione, perché Giovanni è nato nel 1958 e purtroppo si è spento all'età di 38 anni durante un'escursione sul Gran Sasso. Giovanni era stata una figura appunto emblematica in questo settore perché appunto ha sviluppato insieme anche ad altri colleghi, ma comunque anche una notevole dose di energia, di originalità, di capacità individuali, un settore scientifico che riguarda essenzialmente, in gran parte, ma non solo, l'applicazione delle tecniche di grande deviazione a vari problemi che non riguardano unicamente gli aspetti fisici, la turbolenza, ma anche dei sistemi complessi, sistemi dinamici, eccetera. I suoi contributi sono stati molto innovativi, originali, appunto dicevo, e devo dire che il mio ricordo personale di Giovanni risale all'epoca in cui lui si era appena laureato a Roma e io in quel periodo di tanto andavo a trovare il mio amico Angelo Milpiani, con il quale lui poi ha collaborato a lungo. E all'epoca, diciamo, noi eravamo già, diciamo, senior, tra virgolette, per modo di dire, perché avevamo semplicemente 4-5 anni più di Giovanni, ma Giovanni era arrivato alla fine del percorso di studi quando noi già in qualche modo ci eravamo incamminati su quello accademico. Però ecco, con Giovanni c'è sempre stato un rapporto molto diretto, non è che si sentiva questa differenza, anche perché Giovanni era una persona dotata di grande acume e di una notevolissima capacità anche di stare insieme alle persone, era proprio empatico, a quasi tutti i livelli. Questo non voleva dire che non fosse una persona che amava discutere su quasi tutto, spesso tra l'altro io e lui la pensavo in maniera completamente diametralmente opposta, però era molto piacevole e divertente. Si imparava a discutere con Giovanni Paladin, si imparava tanto, anche non solo di fisica. E quindi io ho questo ricordo di lui come una persona estremamente gioviale, tranquilla, esattamente in qualche modo il complementare di quello che poteva essere la Volpiani, la cui umiltà, diciamo, è ben nota a tutti, non credo dire niente che lo offenda, lo dico in totale completa amicizia. Giovanni era esattamente in qualche senso il suo complemento, diciamo, e quindi era anche una persona da questo punto di vista piacevole. A volte abbiamo passato giornate a discutere davanti a una lavagna di questioni che spesso e volentieri sconfinavano anche non solo nel filosofico, ma in cose addirittura metafisiche, ma giusto per divertimento. Diciamo, ci si divertiva a lavorare su queste cose. E questo è importante ricordarlo perché questa generazione di persone, poi appartenuta anche Giovanni, in qualche modo è uscita un po' da quelli che erano gli schemi, i canoni della fisica teorica di quegli anni, che era fortemente improntata nella direzione della fisica delle alte energie, no? Teoria dei campi, interazioni fondamentali, normalizzazione, eccetera. E c'era un numero abbastanza crescente di persone che si muoveva ormai in terreni completamente nuovi. Giovanni è stato sicuramente da questo punto di vista uno dei pionieri che ha sicuramente contribuito a creare questa area, no? Che praticamente oggi la vediamo che ha assunto delle caratteristiche abbastanza, diciamo, diverse da come era iniziata. Vorrei anche ricordare che Giovanni ha dato dei contributi molto interessanti e importanti anche nelle applicazioni per sistemi dinamici alla fisica. Ora non sto qui a elencare tutti i suoi metodi scientifici, ma ben sicuro sono molteplici. E a volte leggere anche solo i lavori è di qualche, ancora oggi di notevole istruttività per i più giovani. Detto questo, lascio la parola a Marco, al quale colgo l'occasione, visto che si avvicinerà alla cattedra, di dare il diploma, perché ovviamente il premio non si ferma a questo, ma diciamo la parte più concreta arriverà al tempo debito.
Grazie. Niente, volevo prima di tutto ringraziare la Commissione, la società e ovviamente per il premio ne sono molto contento, anche conoscendo diciamo, la storia e le motivazioni per cui il premio è stato creato, quindi vi ringrazio tutti, insomma. E adesso inizio. Okay. So I think that now I need to switch to English. In this seminar, I will present some of the results of my PhD thesis, so not all, but some of them. And during my PhD, I focused on the study of epidemic spreading on adaptive temporal networks. And today I'm going to present some results on the effect of stochastic sampling for the control of epidemic spreading. And what I'm going to show you is the result of collaboration with Alessandro Raffaella, who are here, and Vittoria Polizza in Paris, and Claudio Castellano in Rome. And I will make a short introduction at the beginning on epidemic spreading on temporal networks and adaptiveness. Then I will present the first of our results, which is a general formalism for adaptive activity-driven networks, and how this formalism allows us to describe several kinds of adaptive behavior. And then I will present one of the main results of the PhD, which is the characterization through this model of two procedures for contact tracing that are manual and digital contact tracing. What is the role of the sampling of contacts in the control of epidemic spreading. We know that a lot of systems in nature, physics, and human activity are composed of many interacting elements, and some of these systems are characterized by interaction that are not fixed over time, but they are created and recreated or destroyed over time. And so these kind of systems can be described through temporal networks that are networks in which the nodes represent the element of the system, the interaction are represented through links, which are continuously destroyed and recreated over time. And the temporal dimension of this network needs to be taken into account if we want to describe this system, but also if we consider a dynamical process that occurs on top of this network, because if the time scale of the two processes are comparable, the network evolution cannot be neglected when describing a dynamical process which is unfolding on this kind of structure. And this is the case of epidemics, because we can see an epidemic as a stochastic process that occurs on top of the human interaction network. And in this case, we have that the network of human interaction evolves over time, and the time scale of the two processes are comparable. So we need to take into account the temporal evolution of human interaction to describe in a correct way the epidemic spreading. And from a mathematical point of view, an epidemic model is typically described through a compartmental epidemic model in which the population is divided into compartments depending on the health status of the node, and specific rules describe the transition probability. So, for example, we have susceptible infected recovered model in which the node can be susceptible, can be infected with a certain probability, or can recover with a certain recovery rate. And this kind of model typically feature a dynamical phase transition between a phase in which the epidemic do not spread, so an absorbing phase, and an active phase in which the epidemic do spread. And when we are studying an epidemic, we are interested in how the epidemic evolved in the active phase, so when the epidemic do spread, and in the critical point of the phase transition, which is typically expressed in terms of the effective infection rate, which is the ratio between the infection probability and the recovery rate. So we are interested in the behavior of the epidemic in the active phase and in the critical point of the phase transition. And this is quite important when we consider, for example, some intervention, because we want to move the system under the epidemic threshold, so in a regime in which the epidemic do not spread. And this kind of model have been studied at first on static networks, showing how the network topology affects the epidemic spreading. In particular, there are a lot of rigorous results on the fact that the epidemic threshold depends on the topological properties of the network. And so we have the structure of the interaction affect the epidemic spreading. And only recently there have been obtained some analogous results for temporal network, showing that in a similar way, the epidemic threshold depends on how the network evolves over time. And so the network evolution affects the epidemic threshold and in general, the epidemic process. So this shows us that we have a coupling between the epidemic process and the network dynamics, which we need to take into account. But as we have experienced in the last few years, when an epidemic starts spreading into a population, the population reacts with a series of adaptive behaviors, and so adapt to the presence of the epidemic, in a way creating a coupled dynamics on another level. Indeed, as we have seen, for example, when an epidemic starts spreading, the symptom onset or the risk perception change the way people interact, and this has an effect on the network evolution, introducing some adaptive behaviors. And so this requires the use of so-called adaptive temporal networks, that are networks that not only evolves over time, but their evolution is coupled to the epidemic process, or in general, a dynamical process that occurs on top of the network. And in this way, we have a feedback loop, because we have local dynamics, which determine the dynamical state of the node. This dynamical state changes the way people interact, and so change the topological dynamics, which affect the local dynamics. And so in this way, we have the network that evolves over time. Its evolution affects the epidemic spreading, which modify the way the network evolves over time. And in this way, we have a coupled dynamics of these two dynamical processes, which makes the this kind of system quite interesting, both mathematically, but also for real implementation in the real world. And so this is the framework in which the thesis started. And so our idea was that of creating propose a general formalism for an adaptive activity-driven network, so an adaptive temporal network, with the aim of describing some adaptive behavior observed during influenza-like illness. And so we start from the activity-driven network, which is an empirically validated network, since it allowed to describe and it allowed to be treated also analytically and also numerically. And so we consider the activity-driven network with attractiveness, in which each node represents an individual and is assigned with two parameters that are the activity and the attractiveness of the node. And the activity of the node gives us information on the propensity of the node to engage interaction. And while the attractiveness of the node gives us information on the propensity of the node to receive interaction. And in particular, the activity sets the activation rate with which a node activates over time with a Poissonian activation dynamic. And when the node is active, the node creates links with the other node into the population, and the probability for a node to receive a link from an active node is proportional to its attractiveness. And you can see in this video how the network evolves over time. So the interaction are instantaneous, and in this case, we do not consider any kind of memory. At each time step, all the correlation are destroyed, and the model in this way is mean-filled. But as you can see, we are keeping in mind the temporal dimension that we mentioned before for this kind of network. And in general, the activity and attractiveness are jointly distributed, and it has been observed in several systems for interaction that the attractiveness of a node is typically positively correlated with activity, and the activity is typically heterogeneously distributed. This means that in this kind of, if we consider this kind of networks, they could be characterized by hub that are nodes with a high activity and a high attractiveness, and which in the presence of an epidemic could behave like superspreaders. So this is the model without adaptiveness. That is a temporal model. And our idea was that to implement in this model some adaptive behaviors. And our idea was that since the behavior of each node is fully described by its activity and attractiveness, we can think that in the presence of an epidemic, a node changes its behavior by changing its activity and its attractiveness. And for example, we can think that when a node is infected, the node will reduce its activity due to the symptom onset, and will reduce also its attractiveness because of the risk perception by the other nodes who susceptible try not to contact infected individuals. And so what we think is that we can assign to each node, for example, for the SIS model, 4 parameters that describe the behavior of the node when the node is susceptible, so the activity and the attractiveness when the node is susceptible, and when the node is infected, activity and attractiveness. But this clearly can be introduced also for more complicated behavior by adding more parameters. For example, for the SIR model, we will add also the activity and the attractiveness when the node is recovered. And in general, we assume that these 4 parameters, which describe the behavior of a node when the node is susceptible or infected, are drawn from a general joint distribution. And in this way, we are able to describe several kinds of adaptive behavior. For example, we can describe the fact that a certain fraction of the population is isolated when infected by putting to 0 their activity and attractiveness. But we can also describe like more weird behavior, like the disease parties, which are events that has been observed in the COVID-19 pandemic, but also before in other pandemics and other epidemics. And the idea is that there is a small part of the population who, when is infected, increase their activity and their attractiveness in order to propagate the infection or to catch the infection if they are susceptible. And so since we are considering a completely general distribution of activity and attractiveness, we are able to describe several kinds of adaptive behavior by fixing the shape and the structure of this joint distribution. If we consider the SIS or SIR model, we are able to obtain analytically the epidemic threshold for this kind of adaptive activity-driven network through an activity attractiveness-based mean-field approach. and which holds for arbitrary distribution of the activity and attractiveness parameter. And as you can see, a crucial role in the epidemic threshold is played by the cross-correlation between the behavior that a node has when susceptible and when infected. And for example, we can see that superspreaders are nodes who are very active and attractive, both when they are susceptible and when they are infected, because in this way they have a high probability to get infected and then to transmit the infection. And so this model, as we have seen, is able to describe several kinds of adaptive behavior and can be treated both numerically and analytically. But this was, I would say, before COVID. Then COVID starts spreading, and as we know very well, we experienced several kinds of adaptive behavior and control and containment measures that have been implemented in order to reduce the epidemic spreading and the COVID-19 spreading. So we have experienced, for example, extended lockdown, and from our perspective, the lockdown can be seen as a complete stop to the network evolution. So no more links are created and no more links are generated over time. But we have experienced also other kind of control and containment measures, which are essentially adaptive behavior like contact tracing. And in general, all these adaptive behavior that and measure for the control of the epidemic, which have been implemented for COVID-19, were based on the main properties of COVID-19. For example, a lot of infection occurred during super spreading events. So one of the adaptive behavior that was implemented as a control measure was that to avoid the social events of a size higher than a certain higher than a certain group size. Another properties of COVID was a medium-high basic reproduction number, but one key feature was that a lot of transmission were occurring through presymptomatic or asymptomatic transmission. And in particular, this property of COVID-19 requires the implementation of contact tracing. And so starting from this, we apply our general formalism that I described before to describe some of the adaptive behavior and of the control measure implemented during COVID-19. For example, we describe active and inactive quarantine, that were two types of quarantine that were implemented in the early phases of the pandemic. And today I'm going to present you in detail the results of on contact tracing. And in particular, we apply again this formalism to describe manual and digital contact tracing and to characterize their differences. Indeed, contact tracing is one of the main control mechanisms that were implemented with the idea of being able to break the chain of infection without implementing a lockdown, so without stopping the network evolution. And the idea is that starting from an index case, so an individual who's found to be positive, look at the history of its contact in order to identify infected individual, isolate them, and so remove them from the population and from the disease propagation. And clearly, from a modelization point of view, this is quite challenging because, as we have said, we have the network evolution, the epidemic spreading, which are two dynamical processes coupled, and also the tracing process is another because the tracing, of course, on the history of contact. And so our idea was that to describe contact tracing through our model, so extend the model in order to describe contact tracing, and especially we were interested in characterize two contact tracing procedures, the manual tracing and the digital tracing, which were two procedures proposed at the beginning of the pandemic. And there was a lot of discussion about their properties, their advantages, and in particular, their relative effectiveness in reducing the impact of the epidemic. So for manual tracing, we consider the traditional tracing procedure in which, starting from an index case, there are some staff from hospitals who interview the index case and ask the index case to compile a list of contacts that the index case had meet in the time window in the past. Then the contact tracer will contact each of these individuals in the list and ask them to take a test and to isolate. Clearly, this contact tracing procedure is characterized by some properties. For example, it depends on the memory of the index case, and from our perspective, each index case will remember a certain fraction of the contacts engaged in the past that we call recall probability. Also, all this procedure is characterized by some delay because of the manual procedure and the manual implementation of collecting the list of contacts and contacting each of them in a traditional way, so by phone. And the final aspect is also the fact that this contact tracing procedure is characterized by a limited scalability. So if the number of contacts is too high, this procedure becomes too ineffective, is not able to be activated when the number of contacts is too high because of the manual implementation of this procedure. So at the beginning, during the first phases of the pandemic, also another procedure that is the digital procedure were proposed, and the idea is that of using smartphone. If individual need to download the tracing app, and through privacy-preserving algorithm, two devices who downloaded the app are able to exchange some signal when they are close. And in this way, if an individual starts to feel sick, is able and is found to be positive, is able to activate a notification procedure on the app, who is able to send a notification of exposure to all the devices, and so all the individual who entered into contact with the index case, and so with the positive case. This kind of procedure were proposed with the idea of reducing all the delay which were present in the manual tracing because of the automatic mechanism of notification, and also because of the fact that this kind of system is completely scalable, so there is no problem linked to the limited scalability which were present in the manual tracing. And in the discussion that were arising in the due to the implementation of digital contact tracing for COVID-19 spreading, one of the critical points of this procedure were the low app adoption level. So the fact that not all people in the population were downloading the app, and that this fraction of people downloading the app were very low. So this was the discussion, but our idea was that there is also an intrinsic difference in the way manual contact tracing and digital contact tracing performs the sampling of the contacts, and so they explore the contacts. And this difference was not previously highlighted when discussing about the differences between manual and digital contact tracing. And our idea was that the manual tracing performs a stochastic sampling, and in particular, the sampling of contacts occurs on all the possible links in the network. In a way, in an annealed configuration, because in starting from an index case, all the links the node engaged in the past are traceable with a certain recall probability that we call epsilon. While if we consider the digital tracing, the sampling of contacts is localized on a subnetwork of the real network, because only the link between a couple of nodes who downloaded the app can be traced. And so in a way, we are in a quenching configuration. On the one side, we have a sampling that can occur on all the links in the network. And on the other side, we have the tracing that can occur only on links that are between a couple of nodes who downloaded the app. And so even if we assume the same probability to trace a single link, so epsilon, that is the recall probability in the manual tracing, is equal to f squared, that is the app adoption to the power of 2. We fix this in order to compare the two mechanisms in the same condition of probability to trace a single link. We can see that this intrinsic difference between manual and digital contact tracing in a way favor manual tracing over the digital one. For example, if we consider a two nodes interaction in which an asymptomatic node infects a susceptible one, producing an infected individual who will later develop symptoms and activate contact tracing. In the manual tracing, this source of infection will be traced with probability epsilon, while in the digital tracing will be traced with probability f squared. So if we fix epsilon equal to a square, the source of infection is traced with the same probability. But if we consider a three-node interaction, so the same node infects two susceptible nodes, and both of them develop symptoms, the probability to trace the source of infection, even assuming the same probability to trace a single link, is always higher for the manual tracing compared to the digital tracing. And so this is a simple example of how this intrinsic difference in contact sampling could favor manual tracing over the digital one. And so our idea was that to build a complete model, so do not consider only two or three nodes interaction, but consider a complete network, and on top of that, a complete epidemic model, in order to observe from the active phase of the epidemic and also from the epidemic threshold, if our intuition about the intrinsic difference between manual and digital contact tracing is true, and also if realistic problems of manual tracing, such as delays and limited scalability, could make the digital tracing better than the manual, even if the way they perform the sampling is different. And so to do so, we consider again an activity-driven network, but we consider a more complex epidemic model in which a node can be susceptible. The node can be infected and can follow an asymptomatic route, so become asymptomatic, or become presymptomatic and after some time develop symptoms, and then all infected symptomatic and asymptomatic recover with a certain recovery rate. We consider this epidemic model on the activity-driven network proposed previously, and so to each node we have several parameters that describe the behavior of the node when the node is susceptible, asymptomatic, recovered, or in each of these compartments. And what we assume is that presymptomatic and asymptomatic node behave like the susceptible one, so they are able to spread the infection as for COVID-19, while we assume that as soon as a node develops symptoms, the node is immediately isolated and activate contact tracing. In this way, the node is able to trace asymptomatic individuals in the past, and is able to activate on asymptomatic individual a tracing procedure. So in order to model contact tracing, we need to expand our epidemic model by adding two further compartments that are the trace asymptomatic and the isolated asymptomatic. And so we can assume that when a node that is asymptomatic is identified, the node is traced, and after some time is isolated. We need this in order to take into account some delay that could happen in the between the tracing and the isolation of an asymptomatic node. And so the manual procedure is based on the fact that the symptomatic node will remember each of the contacts that the node engaged in the past with a certain probability epsilon. And hereafter, we will consider that this probability could depend on the activity of the node, in particular on the activity of the node who is activating contact tracing, because we can think that nodes who are very active and so have a very long list of contacts will not be able to trace all of their contacts, but will be able to trace only a small fraction of them. And so this will help us later in implementing this kind of limited scalability of the manual tracing. And we also assume that there is a delay between the tracing and the isolation of the contact. When in the digital tracing, we assume that each node downloaded the app with a certain probability. And again, we consider that this probability could depend on the activity. For example, some survey during COVID-19 showed that this probability is higher for people who are characterized by a low activity, and so they are lower for people with a high activity. And so we can take into account also of this into our model. And we assume that the tracing is instantaneous in order to compare it with the manual tracing where we have some delay. So this is the model. We have this epidemic process on top of the temporal network with the coupling that is given by the contact tracing. And what we do is we apply an activity attractiveness-based midfield approach. So we describe for each class of activity and attractiveness in a susceptible state, the probability for a node to be in one of each of these compartments, taking into account also the one added for contact tracing. And we write down the mean field equation by taking into account the network evolution, the epidemic spreading, and the contact tracing dynamics. So this is just a sketch of the main mean field equations, which are quite complex. These are for the manual tracing, but I will just show you the mean field terms for contact tracing. In particular, we will have contact tracing terms which describe the so-called forward tracing. That is the term which describes how a node is able to trace individuals who have been infected by the node itself, so the index case during the presymptomatic phase. And we will have also the other terms, that is the backward tracing, that is the term which describes the way a node, an index case, is able to trace its source of infection. And so these are the two tracing terms. So what we the same equations can be written also for the digital contact tracing procedure. But what we have done is that we take this equation, we linearize them around the observing state, and we perform a linear stability analysis around the observed state in order to obtain the epidemic threshold of the model. And so the same procedure can be done also for the digital tracing procedure. The equations are more complex because we need to differentiate the equations for nodes without the hub, who cannot be traced, and the equation for the nodes with the hub, who can be traced. But also in this case, we have the contact tracing terms with the backward tracing and the forward tracing. So the possibility for the node to trace the source of infection and also individual infected by the index case during the presymptomatic phase. So by applying the linear stability analysis, we obtain these two close relations for the epidemic threshold. So they are quite involved because, as you can see, they depend on the way the recall probability depends on the activity of the nodes. They depend on all the parameters of the model, so on the delay in the isolation, on the fraction of asymptomatic node. Also here we can see that they depend, the equation depends on the way the probability of downloading the app is correlated to the activity of the nodes. And but these are closed equations for the epidemic threshold, which can be solved in general numerically, and which give us the epidemic threshold for our epidemic model on top of the temporal network when only manual tracing is implemented and when only digital tracing is implemented. And so from them, we are able to extract the epidemic threshold and estimate how manual and digital tracing increase the epidemic threshold. Because when we implement a control measure, the effectiveness of the measure can be provided by how much the epidemic threshold is increased, because by increasing the epidemic threshold, we are able to move the system near to the epidemic threshold or under it. And so the first case that we consider is the simplest possible case. So we just one moment, I recall that these equations are also valid for arbitrary distribution of the activity over the population. So they are completely general for arbitrary distribution of the activity, for arbitrary dependence of the recall probability on the activity of the nodes and of the app adoption on the activity of the node. So the simplest case that we can think of is the case of a completely homogeneous population. So all nodes in the population has the same activity and the same attractiveness. And so the recall probability is constant and also the app adoption is constant. And we assume that there is no limited scalability in the manual tracing and no delay. So we are considering the simplest case. And in this case, we can solve analytically and obtain an explicit equation for the threshold with the digital tracing and the threshold with the manual tracing, which are, again, still a little bit complex. But what we can investigate is the increase in the epidemic threshold that is induced by the manual tracing and by the digital tracing as a function of the probability of tracing a link. So by fixing epsilon equal to F squared. And as you can see here, the manual tracing always performs better than the digital one, producing a higher increase in the epidemic threshold compared to the digital tracing. And this is due to the stochastic to the difference in the sampling that is performed by manual tracing, who performs a stochastic sampling, while the digital tracing is localized on the link between nodes who downloaded the app. So this intrinsic difference between manual and digital tracing, at least in this case, makes the manual tracing more effective in reducing the impact of the epidemic compared to the digital one. And moreover, in this case, we are comparing these two procedures when epsilon is equal to f squared. So we're assuming the same probability to trace a link. But in reality, we can think that the recall probability is almost 1/2. So we are able to trace, or we are able to remember at least 1/2 of our contacts. But the adoption level of the app is lower. F squared is the order of 0.1 in empirical cases, so taking real data of the app adoption in European countries. And so we should, in principle, compare epsilon at a higher value with F squared at a lower value. But even if we consider epsilon equal to F squared, so we are assuming the same probability of tracing a contact, the manual procedure is better than the digital one. So the following step would be that of considering a more realistic population with heterogeneity in the activity distribution. And so we consider a power law distribution of the activity. And what you can see here is that the differences are amplified by introducing heterogeneity. So if we introduce an heterogeneous behavior into the population from the activity point of view, so for the individual behavior, we can see that the differences are amplified, and so that heterogeneity favors the manual tracing over the digital one, amplifying the differences that were already present for the intrinsic difference in the contact sampling. And the idea is that if we have an heterogeneous population, and here we are considering again the case in which the app is uniformly distributed over the population, we will have that some hubs, so nodes who in the presence of an epidemic behave like super spreader, who didn't download the app will never be traced digitally, and so we'll be able to propagate the infection during the epidemic, while in the manual tracing, nodes who are hubs and so have a high number of contacts will be traced preferentially and very easily because they will appear in the list of contacts of many other nodes into the population. And so this is why the manual tracing is better able to identify hubs and to isolate them compared to the digital one. And so this is why heterogeneity favors the manual tracing compared to the digital one. However, up to now, we are neglecting for the manual tracing two aspects that could make it worse than the digital one, and in particular, the delay in the isolation, and also the limited scalability. So at this point, we add also these two aspects of reality. So we assume that the manual tracing is characterized by a certain delay in the isolation, and we also assume a limited scalability, which means that we assume that the recall probability decay with the activity of the node. And this is due to the fact that there is empirical evidence that the manual tracing for each index case is able to trace at most a certain number of nodes that we call KC. And so for hubs who have a lot of interactions and a lot of contacts, they will never be able to trace all the contacts or a huge fraction of them. And so we implement this by considering a recall probability which decays with the activity of the nodes. And as you can see here, the differences between in the increase in the epidemic threshold induced by the manual tracing and the digital tracing are reduced by taking into account the limited scalability and the delay. In particular, there is a regime in which the digital procedure performs better than the manual one. And in particular, this happens when we consider very long delay for the manual tracing, and if we consider very high adoption level of the app. But as you can, these values of the delay and these values of the app adoption are very high and too high and are unrealistic if compared with the true app adoption level and with the true delay of the manual tracing compared to the digital one. So we can also say that since in a realistic scenario we are in this regime, the manual tracing is again better than the digital one. And so the limited scalability and the delay in the manual tracing makes the manual procedure less effective, but in the realistic scenario, this procedure is again more effective than the digital one in reducing the impact of the epidemic. And we also perform some numerical simulation in the active phase of the epidemic. So considering the system slightly above the epidemic threshold for realistic parameter of the model. And as you can see here, this is the most general case with also delay, limited scalability for the manual tracing. We can see that the manual tracing, we can focus on several aspects, for example, on the infection peak, on the duration of the epidemic, and on the epidemic final size. And as you can see, the manual tracing produce a lower epidemic final size, a lower infection peak, and also the duration of the epidemic is reduced. And moreover, and this suggests that the manual tracing is also better in reducing the impact of the epidemic in the active phase of the epidemic, because it is able to reduce the epidemic final size and the infection peak properties compared to the digital tracing. And moreover, also the number of people simultaneously isolated is lower. So this means that the manual tracing not only is able to reduce the impact of the epidemic, but also with a lower cost in terms of the population functionality, because we are able to isolate a lower number of individuals. And so we can say that the results that we have observed for the epidemic threshold analytically hold also numerically in the active phase of the epidemic. And up to now, we have considered manual and digital contact tracing as two distinct processes, but they could be in principle put together in a realistic scenario, and that's how it works in reality. But clearly this makes the model much more complex, because we have again equation for nodes with the app and without the app, but node with the app will be able to be traced both manually or digitally. So if a node who activates contact tracing doesn't download the app, will be able to trace the other nodes only manually, but if the nodes download the app, will be able to trace other nodes both manually and digitally. And so this requires to add new compartments to the epidemic model in order to take into account the different timing in the isolation if a node is traced manually or digitally. So the equations are more complex, but again, we can write down the midfield equation and obtain analytically the epidemic threshold. And in this plot, again, I studied how much the epidemic threshold is increased by the hybrid contact tracing process as a function of the recall probability and of the app adoption level, the square of the app adoption level. And we can look, for example, at section of this heat plot, and we can fix, for example, in this case, a realistic value of the recall probability. So we consider to have implemented the manual tracing at a certain level and add to it digital tracing. And as you can see, if we add to manual tracing digital tracing, we have an increase in the epidemic threshold, which is quite slow with the increase in the square of the app adoption. So if we want to obtain a significant increase in the epidemic threshold, we need to consider very high level of app adoption. But in any case, we have an increase, so digital tracing could help manual tracing. But if, on the opposite, we consider a realistic value of the app adoption level, and to that we add manual tracing, we can see that the increase in the epidemic threshold is much faster than the increase given by the digital tracing, and so is enough a very low level of manual tracing and so recall probability to produce a significant increase in the epidemic threshold. So this suggests that again, manual contact tracing, that digital contact tracing could help manual contact tracing, but manual tracing need to be and to have a crucial role in any kind of control strategy based on contact tracing. And so with this, I sum up what I've explained up to now. So the idea that is that during the thesis, I focus mainly on epidemic spreading on adaptive temporal networks. That is an interesting problem because of the coupled dynamics between the network evolution and the epidemic spreading, and the coupling is at several levels. In this framework, we propose a general formalism for adaptive activity-driven network, which allow us to describe several kinds of adaptive behaviors. And this model can be extended to describe contact tracing procedure. In particular, we characterized the manual procedure and the digital procedure, both focusing on the epidemic threshold and on the active phase of the epidemic, by showing an intrinsic difference in the way manual and digital contact tracing performs the sampling of contacts, and so the contact exploration, and by showing an the role of heterogeneity in the agent behavior in these differences. And finally, we show the relevance of manual tracing in any kind of hybrid contact tracing process. And clearly, this kind of approach could be extended in order to take into account more elements for making the model more real, like multiple step contact tracing, or use this information to optimize the integration of these contact tracing protocols in order to optimize the resource allocation for digital and manual contact tracing. And with this, I finish, and I thank you for the attention.
Variant of the epidemic of pandemic. Is this true? And there are consequences on your calculation of the exams on it?
Yeah, the
Sorry, but you're right.
yeah.
Some comment, not at the beginning, probably by
Okay, here. Yeah, in the model, the parameter that so that here delta is the fraction of symptomatic individuals or asymptomatic individuals, and this depends on the variant and on the epidemic taking into account. And also lambda is the probability of infection, and also this depends on the, and typically also the recovery rate depends on the epidemic. So all these parameters, we fixed it for COVID-19 parameter in the original strain, so the first version. But all these parameters are then in a way summarized in the control parameter of the phase transition, which takes into account both lambda and mu, and give us information of how much the system is above the epidemic threshold or under it. But yeah, in the model, they are inside the parameter which give the probability of transition between each compartments.